We're going to be taking a look at this lab, reflected cross-site scripting in a JavaScript URL with some characters blocked. This is straight up a very difficult lab. There's a requirement for some underlying knowledge in order to understand this exploit. And for that reason, we're going to start with the payload and work backwards. We can see the payload here after the query string. Here we've pasted it into burp decoder just so we can see the URL decoded version of the exploit. So we have the initial part of the query string, which is the post ID. We then have the ampersand. We then have a single quote and a closing curly bracket. This is going to allow us to inject into the JavaScript since we are inside curly brackets. We then have a comma. The reason for the comma is we are providing arguments to the fetch API. So we're providing a comma separated list of arguments. In fact, we're providing more than we're supposed to. We'll get to that a little bit later. So we have a comma, x equals x. We're actually declaring an arrow function in JavaScript. We're binding it to x. Now, typically, we will see regular brackets being used as part of an arrow function declaration in JavaScript, but those are actually going to be blocked by the page. It turns out you don't need to use the left and right brackets. So we can simply have x equals x, arrow, then we can open up our code block. Inside the code block, we are using the throw statement. We're actually passing two values. Value 1, Onerror equals alert, and then we're also passing the value 1337. Notice that it's passed as a comma separated list. More on this a little bit later. Notice we also have an open and close comment character in between throw and Onerror equals alert. The reason for that is we can't make use of spaces. So this is a way of spoofing a space, open and close comment. We're then closing our code block, we're then using a comma. So we're now passing another argument to the fetch API. That is toString equals x. We then have window plus two single quotes as another argument. We then have a final argument, which opens a new curly bracket. We have the value x, a colon, and then we have a single quote. Now, the last part of the payload here is really just to tidy up the JavaScript so we don't have an error. We're going to break this down into two sections. So this last part here is really to do with the injection itself to make sure the exploit is injected cleanly. And so is the first aspect of this payload, the single quote and the closed curly brackets. Those are to do with the injection itself. We are just going to focus on the exploit logic first of all. That's everything starting from x equals x, the arrow function, all the way up to window plus and two single quotes. In order to break this down, we're going to fire up a blank HTML document. Okay, we have a blank HTML document. We have a h1 my awesome page. We've opened up some script tags. We're going to experiment so we understand the mechanics of this. First of all, let's start with the JavaScript throw statement. We give it a value, which it then uses as part of an error output. So for example, if we have throw 1337, we are going to throw an error. It's going to have that value 1337. So here is our HTML page in the browser. Notice in the dev console, we have this message, uncaught 1337. Now, the next question is what happens if we provide a comma separated list? And this comma is a type of operator, and all it does is return the last value or the last expression as part of the statement here. So everything together, this is a statement, but it's being comprised of individual expressions that return specific values. And in this case, it's going to return the last value in the comma separated list, the last value in the statement. So if we have throw 1337 and 1338 as a comma separated list, the error is going to throw the value 1338. Okay, we're here with the browser again. Let's refresh the page. You can see we get uncaught 1338 with no reference whatsoever to the 1337. Basically, we can pass as many values as we want as part of this comma separated list. Only the last value is going to be returned, but we can use the other items in the comma separated list to perform various functions. So as an example, let's create a variable. Let's call it letMyVar, and we're going to assign it the value 1. And we could use myVar as the value that's going to be thrown as part of the error. So if we refresh the page, we get the value 1 thrown as part of that error. But we could actually change the value of myVar in the first value we provide to throw. So we can simply say myVar equals 1337. Let's now refresh the page. You can see we get uncaught 1337. Okay, so returning to our payload, notice we have throw. We have a comma-separated list with 2 values. We have 1337 as the value that's actually going to get thrown. And we have an assignment as the first value. That assignment is Onerror equals alert. So the next obvious question is, what is the function of Onerror equals alert? Well, what is Onerror first of all? It's actually JavaScript's error handler. And we know alert is the built-in JavaScript function that causes a pop-up in the browser window with a specified message. In other words, we are overwriting part of the default behavior of JavaScript. Onerror already has its own very specific function, and we are overwriting that by saying it should have the same function as JavaScript's alert function. So anytime Onerror event handler is triggered, we're actually going to get something to do with the alert function in JavaScript instead. Of course, when is Onerror event handler going to be triggered? Well, it's certainly going to be triggered when we make use of JavaScript Throw, because we use throw when there's an error. So rather than get our standard console output with uncaught and then the value of myVar, it's simply going to pass this last value in the comma-separated list to the JavaScript alert function. So let's demonstrate that. We're going to get rid of myVar, which is going to hardcode 1337. So all we have here is a simple throw statement. We have set the Onerror event handler to be the same as the JavaScript alert function. Then we've passed 1337 to throw, which triggers Onerror. 1337 is then going to be passed to JavaScript alert. Let's refresh the page. Notice we don't get any uncaught message in the console. So we don't get the default error handling behavior of JavaScript. We actually have uncaught exception 1337 passed to the JavaScript alert function itself. Returning now to the payload, note that all of the logic we've just considered is actually inside a code block. So let's deal with this x equals x part of the payload. Let's head back to our JavaScript. Now, all this is an arrow function in JavaScript. In full, we'd see it written like this: x equals, we then see a function that takes in a parameter. Then we'd have our code inside the code block like so. And of course, we need the arrow since it's an arrow function. Now, assuming that our arrow function doesn't make use of the arguments, and we can see in this case, it clearly doesn't make use of x anywhere inside the function, we often associate arrow functions written with this syntax: let x, where x equals the name of the function, equals, we then have open and close function scopes, we then have the arrow itself, we then have the code block. The problem we have is that these brackets are going to be blocked by the site itself, and what we're left with doesn't make any sense. But by providing an argument here, it's clear to JavaScript that this is still an arrow function, and it's syntactically equivalent to the same thing, but having the scopes around the argument here. The value of the argument itself is really not too important. The only thing that's important in the context of the exploit is that we can't have spaces. So we have the luxury of as many spaces as we want right now, but seeing as this needs to be contained inside the URL, the spaces are going to break the exploit in this case. But what we see on the screen right now is syntactically equivalent, more or less, to what we've seen in the payload. So now when we refresh the page, we are not going to get an alert popped up. That's because the logic is inside a function. So it's only when we call a function, for example, we could call x, that's then going to pop up the alert to the page. Let's just test that out. So we've defined an arrow function. We've then subsequently called it. Now let's look at the next part of the payload, and that is toString equals x. And this is another example of part of the default behavior of JavaScript being overwritten. toString is a method in JavaScript that allows us to convert a data type to a string. But we can see here this code is overwriting that default toString method and instead assigning the value x, which we know is a function, which we've written ourselves, to the value toString. So toString is no longer toString. toString is now our function x. So let's add that to our code. We'll have toString equals x, and then instead of calling the value of x or the function x, we can then call the toString function. Let's save that. Let's refresh our page. We get exactly the same results. So the next question is, when does JavaScript make use of the inbuilt toString method? Because whenever it does, it's actually going to be calling the x function instead. And that's what the next part of the code is designed to induce. So we have window plus and two single quotes. In other words, we are performing a string concatenation. We're taking window and we are adding an empty string to it. Now, window is not a string. So in order to perform string concatenation, what is the JavaScript going to do? It's going to call that toString method on the window object. But instead of get the default behavior of toString, it's going to get the overwritten behavior, which is actually that x function. In other words, it's this window plus two single quotes that actually calls the x function because it calls toString, which is really the x function. So let's test that out. Rather than call toString directly, we'll simply make use of window plus, and we're going to concatenate an empty string. Under the hood, JavaScript's going to try and make use of the toString method. Let's refresh the page. JavaScript makes use of toString, which is really the function x. Now we get our alert popped up to the page. So that's actually the whole logic of the exploit here, starting from defining the function x, setting Onerror equals alert, setting toString to the newly created x function, and then forcing JavaScript to use toString with the window plus empty string concatenation. That's just part of the exploit though. We want to understand how the injection side of things work here. And in order to do that, we need to dig into the lab JavaScript. Okay, so we're here in the lab. It's a blog and we can view any of the posts on the blog. And notice in the URL query string, we have post ID equals 5. So we have a post ID parameter, and it's this particular parameter that's vulnerable. Let's take a look at the context of this. Let's search for that post ID parameter in the JavaScript. See, there are two matches. We're interested in the second match because that is embedded inside some JavaScript. So what's happening here with this JavaScript? Well, it's calling JavaScript from inside a href attribute, making use of JavaScript colon. So everything after that colon is JavaScript, and we see the fetch function being used. So this is part of JavaScript's fetch API. It's for dispatching HTTP requests to various URLs and manipulating the response data. So it's a common and frequently used part of JavaScript. And it's designed to take some parameters. So for example, the first parameter or argument here is the URL itself. So we can see a HTTP request is being dispatched to /analytics. We then have a comma, so that indicates the end of one argument. We then go on to the second argument, which is to provide data regarding the request. It's a configuration option. You can see some examples of how this might be used here. We have method, then we have the value post. In other words, this is a post request. We then have a body and we have a value that's to be included as part of the post body. We can see the URL encoded post ID equals, we have the value 5, and we are going to inject into this part of the JavaScript. So the context here is that we are inside the configuration options object argument of the fetch method. And the idea is we're going to break out of that configuration option and start providing additional arguments to the fetch API. Now, fetch is presumably only supposed to take 2 arguments. But the idea here is we are definitely planning on providing many more arguments than the fetch API would expect. So naturally, the way arguments work, they're just a comma separated list. And I'd like to just demonstrate this. Let's create a function, we'll call it myfunc, and it's going to take 2 arguments. It's going to take argument A, it's going to take argument B, and all it's going to do is return the added value of these 2 arguments. So it's going to return A plus B. And as an example of using this, let's console log this so we can see the results. We're going to call myfunc, and we're going to pass the values 1 and 2. So let's refresh the page here, and we are expecting to see 3 console log to the page. So we have a function. Let's pretend it's the fetch API. Let's pretend it's only supposed to take 2 arguments as our myfunc is. What happens if we give it a 3rd argument? So it's supposed to take 2. We've just given it 3 arguments. So the question is it going to error out? Is it just going to take 2 of those arguments? If so, which 2 is it going to take? So simple experiment to find out about how JavaScript works. So let's refresh the page. We still just get 3. We don't get any kind of error from the browser. It doesn't seem concerned that we've provided a 3rd parameter. In fact, we can just continue providing arguments to this function. So long as the syntax is correct, only the first 2 arguments are going to be considered when processing that function. So you see we get the value 3 every time. We can provide as many arguments as we want. The thing that makes this especially interesting is that we can also make use of functions and JavaScript expressions. To give an example of this, let's provide a variable. We'll call it myvar, and we're going to give it the value 1. And also, at the end of the script, going to console log out the value of myvar. Let's refresh the page. So we get 3, that's our function call. Then we get the value 1 echoed to the page, that's our value of myvar. What happens, however, if in one of these, let's call them dead arguments, because they're not really used for anything, they shouldn't really be there. What if I use one of these arguments to change the value of myvar? So I'm just going to say myvar equals 10. The question is, what are we going to console log at the end of this script? Is it going to be our originally defined myvar equals 1? Or is this reassignment going to work despite being provided in a fairly unorthodox location in the script? Let's find out. Let's refresh the page. So we get 10 console logged to the DevTools here. In other words, this was successful. It shouldn't have been there. This was a function that only takes in 2 arguments. We provided 6 arguments, and one of those arguments, one of the ones that shouldn't have been there, has reassigned the value of myvar to 10. So the idea with the fetch API is typically we would provide 2 arguments, but so long as we've injected into the fetch API, we can add as many arguments as we want by means of a comma separated list. And furthermore, those arguments we provide can have modification effects on the code, for example, changing the value of a certain variable. So returning to the payload, first of all, we have an ampersand. So in browser terms, that indicates the next key value pair as part of the query string. Now, the interesting thing here is if we try and inject the single quote directly, it actually breaks the page, because part of the page or part of the query that's sent to the backend is simply looking for a number. So it appears that the ampersand allows the page to continue working, but the injection attack itself begins at the single quote. So the single quote closes the string that we're part of. The right curly bracket closes the configuration option of the JavaScript fetch API. We can then start adding parameters or arguments to the JavaScript fetch API. So this is why we have a comma separated list. So our first argument creates a new function. We've seen how this works already. Of course, we can't have spaces inside the URL, at least not for this lab. That's why we have to make use of a comment character. It's a way of spoofing a space. By the way, if you were wondering why we can't just use throw directly, it's because throw is a statement. It doesn't have a return value and therefore can't be passed as an argument to the fetch API. whereas we define a function which does have a return value, the function itself. We then have a comma, so we're passing another argument to the fetch API. This one assigns toString to our newly created X function. We then have another comma. This is now another argument as part of the fetch API. That's window plus double single quote. That forces the use of toString under the hood. We then have a final argument, and the only purpose of this final argument is to end the attack gracefully, because at the moment, we are still going to have a trailing single quote and close right bracket. Remember, we originally started inside that configuration options object argument passed to the fetch API. So we're still going to have in the JavaScript code a trailing single quote and a closing right bracket. So by initiating a new object here with a left curly bracket and an opening single quote, it allows us to absorb that trailing single quote and closing right bracket. That way we still have graceful JavaScript that's not going to error out for the wrong reasons. Okay, so let's solve the lab now. We're going to grab the URL encoded version of the payload. We're going to copy it to the clipboard. We are then going to copy and paste our payload. Press enter, and we get the message, congratulations, you solved the lab. Now, if you did solve this lab just by copying and pasting the payload, that is not really the intention or purpose of this lab. Anyone with basic computer skills can copy and paste the payload. The key here is understanding how and why this particular exploit generates a cross-site scripting attack vector. Okay, let's run a little bit of post analysis. We just want to see how what we've discussed is implemented in reality. Now we can see inside the DOM here, we have a few dots that indicate that the code here has been shortened for readability. We don't want that. We actually want to see the full version of everything. So we're going to have a look at the page source. We're going to scroll down until we find the JavaScript script tags. So notice we have the fetch API. We have our standard URL argument. We then have the options object. And notice we've managed to break out of that. We've successfully closed that configuration option. And from here on in, we're just passing different parameters to the JavaScript fetch API. So here is our first parameter that defines our new function X. We then override the default toString behavior in our next argument. We then have that window concatenation, which forces toString under the hood. We then have our closing object. So we've done this specifically so we can absorb that single quote and closing right bracket. So this is valid syntax. Although in some ways it doesn't make sense, perhaps there should be an error that we've passed way too many arguments to the JavaScript fetch API. In other coding languages, there's going to be a problem. We'd get some error message, certain function expected 3 arguments but received 10, for example. But we don't get that here. JavaScript is completely fine with this. And in some ways, it's this ability to write arbitrary arguments that actually makes the exploit possible in the first place. Now, one final thing to mention here is the context of this JavaScript. It's inside an anchor tag, but the idea is that this particular attack takes place inside a return link. So the idea is we click the return link, then the JavaScript in this anchor tag is initiated. Let's take a quick look at the page. So we can see at the bottom of the blog, we have this back to blog option. So this is the hyperlink. When we click here, this is when the JavaScript gets initiated. Look familiar, we have this uncaught exception 1337. We now know exactly how that works under the hood, all of the moving parts, and how exactly it was injected into the page. Okay, so that was definitely a fairly tough lab, in my opinion. And that probably explains why, in my opinion, there's not actually any decent explanation of this exploit online. I could be wrong. Maybe I overlooked something, but certainly for the videos and write-ups I checked, there's some basic information on why the exploit works, but it is basic. And there are certainly videos of the payload being copied and pasted without any kind of explanation. So hopefully this is a satisfactory explanation of exactly what's taking place under the hood. All right, thanks very much for watching, guys. Hope it was helpful. See you next time.